Hello, I'm Mary Page Bailey, Senior Associate Editor at Chemical Engineering Magazine. Thank you for joining us for today's webcast, Improve Reliability, Efficiency, and Reduce Energy and Maintenance Costs with Flow Analysis Software. We hope it will be informative and useful for all of you. Avoiding downtime is a fundamental pillar of operational excellence at any facility. Plant managers must keep a keen eye on costs associated with equipment repair, maintenance, and energy consumption to ensure that production is at its full potential. Advanced flow analysis and simulation capabilities can provide solutions to many of the issues that can hamper productivity and create unnecessary downtime. Our speaker today is Ben Keyser of Applied Flow Technology. Ben is an expert on pipe flow analysis and has worked with engineers to design and troubleshoot solutions for advanced piping and ducting systems. He works with a variety of industries to provide solutions for liquid gas and slurry systems, as well as solutions to mitigate water hammer and surge issues. Thank you, Ben, for joining us today. Listeners will have the opportunity to send questions to the speaker during the presentation, and these questions will be addressed during the designated question and answer period. At the left of your screen, there is an area where you can type and submit questions to the speaker. Feel free to send in questions at any time during the presentation. We will answer as many questions as possible. If you are experiencing any technical difficulty, you can type that problem in the same area at the left of your screen, and someone will assist you. This program will be archived for future viewing. You can use the following URL, www.chemengonline.com/webcasts. With that, I'll turn the program over to our presenter. Go ahead, Ben.
All right. Good morning, everyone. Thank you very much for listening in, and I'm excited to present to all of you today. There are many ways to improve reliability and efficiency in an operation, and today we're going to look at the major advantage of taking a systems approach to these goals with flow analysis software. So, what is a system? It is simply a set of connected things or parts forming a complex whole. There are many ways that the system concept applies to engineering, and we're going to take a deep look at that today. How does that relate? We've got relationships that can be complex and unexpected, and this is on the aspect of components interacting with each other in a system, and it can be difficult to fully understand how they might impact one another during their operation. Cause and effect can be sometimes difficult to define. It's not always obvious how operation of certain components might interact with others. And then all parts must be considered together. This is necessary to get a full understanding of what's going on. A lot of times engineers will focus on one specific component, and there's a lot of information you can miss, and so when you're able to look at things all together as a whole, you're going to gain a much better understanding from that. So that's one of the key things, is that components are usually designed without considering system interactions, and that can lead to some potential issues. And so one of the impacts is when you have your system where the requirements or maybe the system operation changes, oftentimes there's just not enough time that you have to be able to spend evaluating other operating scenarios to ensure they'll work. And so that's another issue with not taking a systems approach. And when ignoring system interaction, it can lead to various issues such as poor system performance. You can have maintenance problems where you're constantly having to repair equipment, high power consumption where you would have a high energy cost because the pumps are operating really hard. high costs, and this includes energy costs, maintenance costs, repair costs, and of course, don't forget about simply the potential loss of profit and potential downtime and product losses. So there's a cost there that's important to account for as well. And so our focus today is going to be within the context of pumps and piping systems when we use the term systems. It's all of the piping and all the components within that entire context there. Now, uh, there's a lot of information here on this Behringer curve, and let's focus on things a piece at a time. So the first thing that is plotted here is the pump curve. It's a typical pump curve where the head versus flow and efficiency versus flow are plotted together, and so you can see those as the pump curve and the efficiency curve. The maximum efficiency of the pump is known as the best efficiency point, and on this graph, it's denoted by the vertical line. You'll see BEP. That's the best efficiency for the pump, which most likely is not 100%. It'd be really nice if it was, uh, but that's for that particular pump the most efficient that it's going to be able to operate. As the pump operates at different flow rates on its curve to the left and the right of the best efficiency point, there are also various operating problems that are identified on this graph. Things such as if you're operating at a very low flow rate far back on the left of the curve, you could have high temperatures and low flow cavitation. Uh, then you can have problems with the pump seals and bearings. You can lead into various recirculation issues. Basically, whenever you're operating away from the best efficiency point, that's what's going to lead to operating problems. And I've heard stories countless times where the pump seal is wearing out over and over, and the operators would typically blame the seal manufacturer. Well, once the seal manufacturer asks, how are you operating your pump? And they find that the pump is actually operating way far away from the BEP, it's not the seal that's wearing out. The pump killed the seal itself. And so this is critical to be sure that you're operating as close to the best efficiency point as possible. Not only is that going to avoid all of the various issues that are denoted on this diagram, it's going to improve the pump's reliability and efficiency as well. Let's take a look at that bell-shaped curve. That's the Behringer curve, and this represents the mean time between failures and is a measure of reliability. So the most reliable of the most reliable point for a pump is going to be at its best efficiency point. And so if you're operating at the best efficiency point, the mean time between failure is going to be the longest period, and you're going to have the best reliability factor where that's where you're going to be operating. So that's what is known as 1 MTBF. So that's going to be the longest time between failure at the BEP. If you were to operate at a flow rate range between, let's say, 80% up to 110% of the best efficiency point, that mean time between failures can dramatically reduce by half. And that's when you're still operating at flow rates from 80 to 110% of the BEP. That's a typical preferred operating range that you will typically see for a pump. Oftentimes, pumps are operating way far away. They might even be operating as low as 20 or 30% of the BEP. And so, in that particular case, the mean time between failure is dramatically reduced even further. So, uh, whenever you're operating your pump system, think of this Behringer curve and have in your mind what the pump curve looks like and the efficiency curve, and then think about what flow rate that you're actually operating at. And if you're operating far away from the BEP, just keep in mind that the system is going to the pump is going to be less reliable in those cases, and you're going to have shorter times between each failure that occurs. There are some important costs to consider here, and they can impact a system in different ways in the design and operating cases. And so these are important things to keep in mind. Number one important thing is safety. So, damage to equipment is certainly costly and a problem, but that damage to equipment itself can also cause potential injury or loss of life to others, and that is even more costly than simply the damaged equipment itself. And here are some examples of some uh, issues that can reduce the safety of the system. Cavitation, either on the pumps or the piping itself, operating at really low pressures. If you have water hammer issues where a valve is suddenly closed really fast, that can cause a very large surge in the pressure in the system and the pipes can potentially burst. If you have pulsation issues, that can cause degradation to systems over time. All of those are different things that can become a potential safety issue. Other situations is your fluid and pipe wall temperatures. If you're operating at a really high temperature process, then you need to make sure that you have plenty of insulation to reduce the service temperature so that if an engineer or an operator is walking by that they don't burn themselves. So safety is the number one concern and it can lead to very significant costs. Next thing to consider is operating costs. This is still significant. However, it is possible to lower your operating, it's still going to be a lower cost than constantly fixing or operating bad designs. And so examples of this include energy costs and maintenance costs and unplanned shutdowns. And so all of these are operating scenarios that you want to try and avoid. Next, we have maintenance costs, and so this would be including various things like your typical preventative maintenance programs, and so it costs something to just continually service your equipment. But let's talk about the situations where things go wrong. Uh, if you're using a flow analysis software, troubleshooting your system to be able to find the root cause of a problem rather than simply treating the system over and over, as an example, replacing pump seal after pump seal after pump seal, it can dramatically reduce your overall maintenance costs. And when you reduce the maintenance costs, another important impact to that is making sure that you're operating your equipment within manufacturer ranges and understanding how your system components interact with each other. And then finally, we have capital. And so this is usually your initial design. And so if you can improve your initial design, that could potentially be more costly up front. But even though it may be a more expensive initial design, if it's designed and operated properly, that in and of itself will help reduce your safety, operating, and maintenance costs in the long run. And so when you take a full system approach, it helps you understand those capital costs and how you can reduce other costs a lot better. Now, getting into the flow analysis aspect of things, what is important when you are trying to build a hydraulic flow model of a piping system? Well, The moral of the story is the more accurately and close to reality that you model your system, the more likely it is for model results to match measured data. And so if it's in the system, you should definitely include it in the model. So things that are important to take into account, fluid properties. You got to make sure that you have the right density and viscosity, vapor pressure, etc., in order to capture the hydraulics in the system. Your piping should, of course, be included with correct diameters and friction models. Length is really important, but when you have a really large, complicated system, do you really need to go out and detail every single pipe down to the 16th of an inch in order to have an accurate flow model? Not necessarily. This is where you still have to apply good engineering practices and good engineering judgment when you're doing flow analysis. When you think of the Darcy-Weisbach equation for frictional loss in a pipe, the frictional loss is much, much more dependent upon the pipe diameter than it is to the length. And so if you absolutely ensure that all of the diameters in your flow model are correct, and maybe your pipe lengths might be off a little bit here and there just due to not detailing down to the 16th of an inch for your pipe length, you could still have a decently accurate flow model. So be sure to keep that in mind. Other things that are important to include is for your tanks or reservoirs, your liquid levels and service pressures will provide a pressure coming into the piping, and so it's important to specify those properly. During a transient simulation, your liquid levels could change. That would be important to account for. As far as modeling your pumps, it's good to be able to specify your pump head curve and flow, or specify an efficiency or power curve. That way, the analysis tool would be able to calculate how efficiently your pump is actually operating. And then including the MPSH curve is also really important, because you don't want to have cavitation inside your pumps, and you want to ensure that you have plenty of margin available between the MPSH that's available from your system and the MPSH that's required for your pumps. For equipment, there's a lot of different ways that you can model the hydraulic behavior through different pieces of equipment. In general, one of the easiest ways is to essentially just model a profile for your pressure drop versus flow, and that'll do a good job at capturing the hydraulic behavior. For valves, you can model CV values and include open percentage data. This is really helpful if you're trying to model control valves in your system, and the analysis tool would be able to figure out how the control valve needs to change its pressure loss to meet set point, and then the CV and open percentage can be calculated if you include that data, which would be potentially critical to your application. Last but not least, fittings, K-factors, equivalent lengths is certainly important to make sure that you're accounting for the minor losses in your system. Now, let's say that you have included all of this information in your hydraulic model, and the flow model results are still not completely matching your measured data. Well, that could be indicative of a few potential different things. Maybe something might not be modeled right, or maybe there's missing data. Maybe from a drawing, you're capturing a certain diameter of piping in a particular header somewhere, and at some point, maybe they changed the piping out in the plant and didn't update the drawings. That would be an example of where something is not modeled right, which just it wasn't known up front when you were building a model. Another reason where model results may not match measured data is potentially the measurement devices might be bad, and you might need to replace those. Or there very well could be corrosion or fouling or various types of degradation in the system that's not accounted for. So all those are reasons why your model results may not match measured data. In that case, something would have to adjust. But long story short, the closer that you model your system to reality and what's actually in the plant, the more accurate your flow model is going to be. Now, this is an example of a flow model for a cooling tower system. It's just a pictorial example of what the piping system might look like with various components. So you can see there's the cooling tower basins followed by four pumps that are operating in parallel, and then there's some heat exchangers further downstream, and then finally they'll discharge out the spray nozzles at the top of the cooling tower. And so this is just one example of what a system might look like. On the right-hand side, that is providing just an example of what the input information might look like, where all of the pipes are labeled for the various runs that they're in. You can see the various sizes and lengths of the piping. Some pipes have additional losses included. So wherever you see those red ampersand, that means those particular pipes, we are lumping in the minor losses with those piping themselves. So that's one way that you can still simplify a flow model and maintain a high level of accuracy, is by including the effective losses from your fittings with the piping themselves. That way you can reduce the amount of clutter that's built into the model. Other things that you can also include in the piping would be elevation changes. So this is still a relatively simple model, but there's a lot of piping in the system that we're going to be able to capture effectively. This is an example of what the results might look like for a system like that. There are some results for the pumps at the top upper left table there, where you can see the flow rates and pressure and head increases across each of the pump, the efficiency that they're operating at, MPSH comparisons, and so that contains a tabular input or format for your pump operating data. Also captures the results in the piping for velocities, flow rates, pressure losses in the pipes. And on the right-hand side, we've captured a profile for the pressure from the cooling tower basin all the way to the cooling tower spray nozzles. And this gives a good picture of how the pressure changes throughout the system. And so there's actually two flow paths that are plotted here. So if we go back to the previous graph, there's two separate paths that are plotted. And if the system is modeled and operated very well and is very symmetrical, then you can see how the results are the same for both flow paths. So just an example of what a flow model and the results might look like. How can pumping systems become inefficient? There are several ways. One is having a lack of standard for designing pumping systems. What we have found is that doing a hydraulic flow analysis is kind of a luxury thing, because codes and standards typically do not require the piping system to be analyzed, if at all. And so the engineering company, if they're not asked by the operators to do a flow analysis, then they have their choice to even completely ignore doing a flow analysis, which is not recommended practice, but it happens. And so the lack of standards for designing pumping systems, that is a big reason why systems become inefficient, because they're not taking a system approach to seeing how the pumps are going to operate when all of the rest of the changes in the system are occurring. And so when that happens, pumps and control valves, they can become oversized. And when they're oversized, it's usually so that their design can meet future requirements, but they're only operating to meet current market needs. So in terms of a pump that's being sized, it will be oversized to meet higher flow rates in the future for potential expansions. But when the pump is set into its actual operation for normal conditions, a control valve downstream might be throttled to meet a lower set point. Well, when you have a control valve, that's just wasting energy right out of the system because you're putting in energy into the fluid from the pump and then you're taking that energy right out with a control valve downstream. That's very similar to driving your car with the foot on the gas and your foot on the brake pedal at the same time. It's going to be very inefficient, and really, it's going to tear the system apart. And so that's a major issue for sure. Other things to lead to inefficiencies is just the overall age of the system, where the wear and tear is going to take its toll. When the process changes or modifications are made to the system, that will affect operation, which can make things inefficient. And then simply a lack of a system approach can hide issues that you wouldn't see if you're only looking at things component to component. So this is where having a system approach to look at everything as a whole is really helpful. So not only is reducing energy efficiency going to lead, or not only is a reduction in efficiency leading to higher energy costs, it also decreases reliability and has significant safety and maintenance costs. And everyone wants higher efficiency, which is really important, but it's not just about efficiency. It's also about safety, reliability, and in a lot of cases, those are even more important. There are several advantages to using flow analysis software, and really it just helps you understand your system and how things are interacting a lot better, especially when you have multiple load cases. If you're trying to see how things are operating in different seasons or potentially different configurations and requirements, when you have various flow paths that are on at certain times and some that aren't. You might have water hammer or cavitation issues. If you're working with a gas piping system, which is outside the scope of this webinar, because this webinar is focusing on liquids, but if you have gas piping systems, you can have issues there too, where you might have choked flow where decreasing downstream pressure is not going to give you any higher flow. And so basically, a lot of money is often spent on operating poorly designed systems, and that can be easily prevented by doing your flow analysis on the front end. So if you have a better understanding of how the whole system is going to interact with itself, it's going to lead to a much better design. Better designs will reduce long-term costs that we've already been talking about: maintenance, repair, energy costs, lost profits due to downtime. There are a lot of other things that you can do with flow analysis software. System sizing is really helpful for the design process from the get-go to properly size your pumps and valves, piping, etc. There are certain situations where you might be starting off with a pilot plant, and then you need to take the pilot plant and scale it up to the full operation. That can be really difficult to do without having a flow analysis tool. And so flow analysis will streamline being able to ensure that your scaled up version of the pilot plant is actually going to work. Obviously, the software will help you quickly determine your pressure, flow, and temperature distribution. Design feasibility analysis is really important with software, and I visited a refinery down in the deep south of the United States a couple years ago, and I was doing a lunch and learn for several engineers at the refinery, and one of the senior engineers came up and told me that they had recently put 2 new heat exchangers into their operation for an expansion. And he asked the senior level management if they had done a flow analysis beforehand. And not only did the upper management say that they didn't do a flow analysis, they actually said they decided not to do a flow analysis. Well, what happened? Sure enough, when they turn on the flows to the new heat exchangers didn't get any of the flow because the pumps were already maxed out, serving all of the rest of the flow demands. So, moral of the story is get it right the first time and take the time to do your flow analysis to prevent future problems and ensure that your expansions and your designs are actually going to work. Other things that you can do is evaluate operation changes. You can do heat transfer analysis, transient analysis. It's a really helpful tool for troubleshooting your system. You can quantify how much scaling or fouling might be built up inside your system. That's an important one. When you're trying to figure out how to make changes to your piping system, it's really useful to have a flow model to help you predict how those changes are going to impact the behavior of your system. But if the system has been in operation for a long time, your flow model would initially be based upon clean piping. So you need to build in the corrosion into your flow model so that your model matches results. And so a good flow analysis software tool would have an ability to be able to figure out essentially how much scaling and fouling might be built up inside your system in order to calibrate your model. Other things that you'd want to capture is your pump and system degradation. If you're modeling corrosive fluids or non-Newtonian fluids or settling slurries, that can degrade your pump performance. It's important to maintain code compliance, and so software can help highlight where your maximum or minimum pressures or velocities for your requirements would be violated. It's helpful for helping you be able to find ways to minimize energy consumption. You do full cost analysis. Water hammer analysis is really important to ensure the safety of your system. You can do force calculations for pipe stress analysis, slurry modeling, pulsation. There's a lot that you can do on having a good flow analysis tool for your system. All right. So now we're going to get into taking a look at a case study for a real system that had some major problems and how flow analysis software dramatically helped improve reliability. And so this is a raw brine injection system for a unnamed chemical plant. And the situation is that the system included 5 vertical pumps and 5 horizontal pumps. And the application was to displace product in a chemical plant's underground cavern storage facility. And one of the main issues that the operators realized is that the pumps were competing hydraulically. Basically, what that means is if you have pumps that are operating in parallel, if they're competing hydraulically, they're going to be having different flow rates through each of the pumps in parallel, where ideally your flow distribution should be as similar as possible. So if you can ensure similar flow rates to pumps in parallel, they're going to operate a lot better with each other in general. So here's what happened is that the plant had 41 repairs over a 5-year period, which ended up costing just under $1.25 million. So repair after repair, like the example of seal failure after seal failure. They kept having problems, and they just kept putting a Band-Aid on the system, essentially. You know, the seal wears out, get another seal. It wears out again, get another one. The bearings fail, get more bearings. All sorts of different repairs. And the average time between total failure was just under 15 months. So massive issues were going on with the system. So the way that the project started was it's always helpful to get a sketch of the system for what it might look like because this will be a guide to how you're going to build your flow model, especially if drawings do not already exist that you could import into a flow model. So if you don't have drawings, then you have to make a drawing. And then this is what their flow model looks like for that brine injection facility. And so this is where the vertical pumps were in the system, and that was the focus of this project, was to try and figure out how to improve the performance of those pumps, because those were the ones that were having the issues. These are the horizontal pumps at other areas in the system, and there very well could have been potential issues with those pumps, but it wasn't the focus of the project. And so the vertical pump was what we were focusing on. This is a crossover valve that led from the fifth pump in parallel in the top right that connected it to the header of the rest of the pump discharge for the vertical pumps. So one of the operating scenarios that they were testing was, if they were to close that crossover valve, would that help improve the overall efficiency and reliability of the pumps? And we're going to take a look at some scenarios to see if it actually helps. Finally, one of the other things that they were tracking when they were doing the analysis was the overall flow rate back into the cavern storage facility. And so there were certain flow and pressure requirements that they had going into the cavern. They needed to ensure that whenever they figured out how to operate their pumps in a certain way, they had to maintain the minimum flow and pressure requirements into the cavern. And so we're going to see that at the results at the end of the case study here. So there are several scenarios that they tested, and one of the scenarios was to keep all the valves open. Another one was to close that crossover valve that I was talking about. And then the third scenario to test would be to ensure that the cavern pressure was maintained at 300 psig, where previously it was operating at different operating pressures in different circumstances. This is the entire list of all the scenarios that they ran, and this is critical to finding a good flow analysis tool. If you're looking for a good flow analysis tool, you want to make sure that it has the ability to model any number of operating cases within a single model. And that way you can make any number of changes to input in any scenario, and you want to have it set up to where there's intelligence built in, so that if I made a change at the test one scenario, that change should be able to pass down to the children's scenarios underneath test one. Hopefully it's obvious that you can see that a good scenario management tool like this operates very similar. It looks a lot like a family tree where there's lineage and different families of scenarios that you can make. And so there are 32 scenarios that the contractor ran to figure out how to meet their model results and match test data in the field. Now today, we're not going to go through all 32 scenarios. I'm going to pick 2 of them. And so if I go back to the previous slide, I'm going to look at the test 4 families, the test 4 family of scenarios, and the test 7 family of scenarios, and give you an idea of what that looks like. So those are the results that I'm going to be comparing. And we're going to focus on the upper part of the system where the vertical pumps are located. And in the different scenarios, you're going to see how the various vertical pumps and flow paths are turned on and off. In the other areas of the model where the horizontal pumps are located, there are several other pumps and flow paths elsewhere that have been turned on and off as well. But for simplicity, I'm going to ignore those other areas, and we're just going to focus on the results in the vertical pump section itself. So here's the first scenario for keeping all of the valves open, comparing the test 4 scenario to the test 7 scenario. So the test 4 scenario has 4 pumps operating. As you can see, the one on the far left is turned off, and there's no flow through that path. That's what the dotted lines in that pipe run means. And then on the right-hand side, this is test 7. And in test 7, we only have 3 pumps that are operating. The 3 pumps on the right-hand side. So if we were to set things up and run this model where all the valves are open, namely that crossover valve, here's the results that we're going to see. So based upon the scenario where 4 pumps are operating, I want you to focus on the overall efficiency as well as the proximity to the best efficiency point. The efficiency values for all 4 pumps are on average around 50% for 3 of them, and then one of them is doing really well at 85%. But when you look at the percentage of the BEP itself, that's the indicator of if you have an issue. So in that particular case, efficiency is not the only answer. You want to make sure you're operating as close to BEP as you can. Again, the preferred operating region is typically going to be 80% to 110% of your BEP. Well, here it's clearly very far away at around 43% of BEP. Only 1 pump is operating at 85%. When you simply turn off one of the pumps, you can see that you have a significant increase in efficiency for 2 of the pumps from about 53% to 58%. But look at the boost in the proximity to the best efficiency point that you get, up to 50% and 93% with 3 pumps operating. That is with only one simple change with turning off one of the pumps. And it's still able to meet the design flow requirements for the cavern. So this is one of the things that you can see on changing your operation to improve reliability of your system. Now, let's take a look at the second scenario where we are modeling 4 pumps operating versus 3 pumps operating. But you can see how now in this scenario, that crossover valve is closed. So in this particular case, the pump in both instances on the far right-hand side, it's not even connecting to the discharge header for the other pumps on the left-hand side. And let's take a look at how this impacts our results. For the 4 pump operating scenario, our overall efficiency is around 50% for 3 of them, and then the percent of BEP is 40%, really, really low. Simply by changing that, or by closing off that crossover valve, we take the proximity of BEP from 40% up to 50%. That's a significant increase that's going to come out in a lot better reliability than it was operating at before. But again, this is just another scenario that they were testing. We're not done yet in finding where things should actually be operating at. So the last scenario that they looked at was, what if they increased the cavern pressure to 300 psi? Well, the system here for each of the pumps looks the same, but we're keeping that crossover valve closed. So we've got 4 pumps running versus 3 pumps running. The crossover valve in each system is closed, and we want to try and maintain a pressure of 300 psi in the cavern. And here's the impact on results. We start off with 4 pumps operating. We're at 56% or so of the best efficiency point. By increasing the pressure, it increases massively up to 72%. Now, that's still not 80% where we are on the lower end of the preferred operating range, but think about the previous scenario where all the valves were open for test 4. With 4 pumps operating, we're seeing proximities of the best efficiency point of all the way down to 40%. So having an increase from 40% up to 72% of the best efficiency point is huge, especially when the pumps are then able to operate at efficiency values of 72%. A, you're going to see a direct correlation to how much money that you would save in energy costs under these circumstances, and a good flow analysis software would actually be able to calculate that for you. And then B, you're going to have much better reliability for your system, less maintenance issues, less repairs, less downtime, overall a lot higher profit that you're going to be able to come away with in those operating scenarios. So here's the overall results for all of the different scenarios that they're looking at. As you can see here in the upper scenarios for test scenarios 2 and 3, they were ranging at even lower proximities to the best efficiency point, between about 20% and 60%. And then all the way up to about 75% in test scenarios 6 and 7. So did a lot better in those cases, while still maintaining the required flow rates into the cavern that they needed. So they're able to not operate all the pumps that they had and still meet their requirements. And that's the flow rates into the cavern that they're concerned about. So in summary here, the software simulation discovered much better flow paths and pump operations to operate at in order to ensure their required flow rates and pressures, and the simulation itself dramatically improved reliability. And then once it's operating more reliable, the software makes it a lot easier to recommend further modifications to the system down the road. So in conclusion here, it's really important to take a system-wide approach for both design and analysis of your new and existing systems. Don't wait to do it until after something breaks or when something's wrong. If you do the system-wide approach beforehand, things are going to work a lot more reliably for you, and it's going to help you understand the understand the system as a whole versus significant limitations if you're only looking at things component by component. And then you can also have a much better method of treating the actual cause of the problem itself, not the symptom. Again, quit just replacing your pump seals, or quit replacing valve after valve after valve. Use a flow analysis tool to help you understand why your pumps or control valves or other pieces of equipment are operating poorly and having problems. Last but not least, go beyond simply go beyond the typical goal of just trying to minimize energy costs. Everybody's talking about efficiency these days, which is really good, and it's important to take into account efficiency, but it's a lot more important to think overall system reliability, maintenance, downtime. If you focus on those things, naturally that's going to improve the energy efficiency and minimize the energy cost itself. Thank you all very much for your time. If anyone has questions or would like to get more information on the flow analysis software tools that we offer at Applied Flow Technology, feel free to contact us. You can contact me directly. My email address is in the presentation slide here, and the presentation slides will be available for you all. And if you'd like to try out the software itself, we'd be happy to arrange that for you. So thank you all again. And with that, I will turn this over for questions and answers.
Thank you, Ben. That was a great presentation with a lot of excellent examples. We've had a number of questions come in from our audience. I'll just start with one asking about how big of a deal is it really to operate pumps far outside of the BEP?
That's definitely a very big deal. I mean, the case study there made it really clear where when they were operating all of their pumps together, they thought that they needed 4 or 5 pumps operating in parallel all at once, and they really didn't. And when they were operating all the pumps, the expectation is that each of the pumps together should deliver more flow where in reality it doesn't. It is a very quick point of diminishing return where more and more pumps do not actually give you that much more flow. And so when they're all competing each other, trying to add more flow to the system, the the multiple pumps together are actually adding smaller amounts of flow to the system. So they are operating further back on their pump curves. And as you saw, in the ranges of 20% to the 50% of the best efficiency point. I didn't have all the details on what specific repairs were occurring, but you could probably guess that their seals were failing, bearings were failing. I mean, pumps might be overheating, leakages, cavitation. There is a lot of issues that start occurring when you're operating away from the best efficiency point. It's just like how when you're driving your car, your car is going to have a sweet spot where it's going to give you the best savings on gas mileage. And if you're not driving your car at that particular speed, then it's going to cost you more in gas money. Well, not only is the gas money important, but if you're operating at that sweet spot where the car is designed to operate at a certain speed, it's just going to work a lot better in the long run as well. So it definitely is a big deal to operate as close to BEP as possible. Otherwise, you're going to see issue after issue. You're probably going to think that it's only a problem at the pump, when really, what's causing that pump to operate so far back on its curve? Maybe there's a bottleneck somewhere. The flow analysis will help you be able to find those things.
Okay, great. Thank you. That was an excellent answer with a lot of good information in it. We've had another question come in asking about the software that says, can you import a piping model from a CAD program or from a third-party stress analysis program such as AutoPipe?
That's an excellent question, and there are some software tools that do not have the ability. The flow model screenshots that I was showing you that we offer from Applied Flow Technology does have that ability to import various types of neutral files. One example is piping component files that come from isometric drawings from various CAD softwares, or neutral files from pipe stress software. You've already taken the effort to build your piping system in other software tools to do different things, and if there was a way that you could bring that into a flow analysis tool, you would want to be able to do that to save you time rather than having to build it all again from scratch. And so with our software, yes, you have the ability to import various neutral file formats from different CAD programs as well as other types of files. And for the cases where, it very well could be where you don't have any drawings for your system and you literally yourself are having to go out and do a line walk of the plant and you're having to build your own drawings. Well, if you build your own drawings in a CAD software, you can import that. But if not, the software tool that you use should also be so user-friendly to where you can quickly build a system where it would still be easy enough without having the import feature if you didn't have drawings that could be imported. Excellent question there.
Yeah, thank you. And kind of in a related vein, we had another question come in asking, how much of your system do you need to model to diagnose a problem, and where can assumptions be made?
Well, it depends on what you're doing. If you're doing a simple steady state analysis, then there are a lot of ways that you can simplify your system to be able to accomplish big things. And so let's say that you have a issue with the pump header, for example, and you don't have very much information about what's going on in the other areas of the system. But if you know what the pressures or flow rates are close to that header and where it leads to, for a steady state analysis, you could essentially break the system at that point and put a boundary condition for a known pressure or a known flow rate at that point, because maybe that's what's being measured right there. And that way you can focus on what's going on around the pumps if you don't have to include everything else, and maybe that might be able to help you solve the issue of what's going on. So for steady state analysis, you have a bit more flexibility on being able to neglect various parts of your system where you could just put a boundary pressure or flow rate. If you're doing water hammer analysis for surge situations, that's a lot different, because if we are doing a example of a sudden valve closure, that's going to cause a high pressure surge that's then going to reflect and propagate all throughout the system, basically at the speed of sound. And so other areas of your system are going to see those really high pressures as well. So if you're doing a water hammer or a surge analysis, it's a lot more important to include those other areas of the system where you can't just put a simple pressure or flow boundary at a certain point, because that pressure and flow rate would be changing in reality over time. And so you'd have to have all the reflection points set up correctly. So it depends on if you're doing steady state analysis versus water hammer analysis. But for both of them, there's other things that you can do. I kind of hinted at it earlier. One example is if you have a whole bunch of minor losses, elbows, valves that are just wide open, orifice plates, area changes, etc. All of those minor losses are going to contribute to the overall pressure loss in your system, and you need to account for that. But rather than cluttering up the model with modeling each of those fittings explicitly as separate components in a flow model, you can easily lump all of those losses into the piping itself, and you're still going to capture the overall pressure loss, but it's going to simplify your model where you can still have a high level of accuracy. So that's an example of where you can get away with being able to simplify things in certain ways.
All right, thank you, Ben. We have time for maybe one or two more questions. So here's one asking, is it possible to include variable speed drives in your models?
Absolutely. There's a couple ways that you can accomplish that. And one way is to simply change the speed directly. If you know that the pump is operating at 80% speed or 70% speed, you can model that explicitly, and the software will automatically adjust your pump curve for you via the affinity laws. Other ways that you can do it is by specifying either a flow or a pressure set point. So maybe you don't know what speed the pump has to operate at to give you a certain flow that you need. Well, you can model a set point value, and then the solver will figure out what speed the pump has to operate at from the affinity laws to meet that set point. And so that would determine what the speed is. In addition, you can also model impeller changes as well. That's another thing that you can modify with the pump. And overall, whenever you're making any of those types of changes, either the speed or the impeller trim, you can capture what the original pump curve and modified pump curve is for the pump, as well as the entire system curve, and you can plot those things together to see where your pump is actually going to be operating in the system.
Great, thanks. I think we have time for one more question from the audience. We have one asking, can this type of flow analysis software be used for analyzing gas flows?
Well, the software that I was demonstrating today and showing screenshots of is called AFT Fathom, and that is specifically designed for modeling incompressible flow for liquid piping systems. So it does have the ability to model low velocity gases that has small pressure losses and no temperature change, but it's going to be using incompressible flow methods. So it's really not the right tool for doing that type of analysis. And there's going to be some potential uncertainties in the results when you're trying to use incompressible flow methods for a gas system, which is going to behave compressibly. We offer another tool that does full compressible flow analysis called AFT Aero, and that will model full thermodynamics of the system, and it's going to take into account all compressible effects, real gases, heat transfer, sonic choking, etc. And so it'll properly model all of the gas impacts on that system, which AFT Fathom itself is not designed to do. Good question there.
All right, well, thank you so much, Ben. That was a lot of excellent information for our audience. We're now approaching the end of our webcast, and to remind everyone once again, this program will be archived at www.kimingonline.com/webcasts. Thank you so much to the speaker, and thank you all for attending. We hope you will benefit from today's presentation. Have a great day.